Alright, this is lesson 6, polynomial functions and end behavior. So if we're talking about end behavior, we're talking about what's happening at the end of graphs. So I'm going to draw this real fast. So end behavior is not what's happening at the origin, it's the opposite. It's what's happening way out here as on the x-axis. We go to positive infinity, or over here if we go to negative infinity, right? These are known, of course, as the inputs on the x-axis, the independent variable. And then we, of course, have the outputs on the y-axis, right? And what happens, we go to negative infinity or positive infinity. So the end behavior is the same as talking about infinity behavior. What's happening at the very end of any given graph? Does it go up? Does it go down? Does it go left? Does it go right? What happens? Okay. So when we're saying something like this, the inputs increase without bound, right? That's a fancy mathematical jargon, right? We just got to translate that. So when we see inputs increase without bound, it's just saying the x values are moving toward infinity. Okay. So like right over here, x increases, that means positive, right? So we get closer and closer to this point right here, positive infinity. If the inputs are decreasing without bound, which means without bound means forever. So the inputs are decreasing forever, we end up with negative infinity, right? So the x values are moving toward negative infinity. Right? And we can do the same phrasing, but with the outputs, which means just the y-axis, right? So we're talking about outputs increasing without bound, right? Outputs, y-axis. We're talking about going up this direction towards positive infinity. So it's the same statement up here as the x values moving towards infinity, but now it's the y values. So the y values, or the f of x. So it's the values, f of x values are moving toward infinity. Right? And likewise, we have the outputs are decreasing, which means the y values, or f of x, are moving toward negative infinity. And that would be down here. So that's just the jargon we'll be using for this, but just know what it really means in our day-to-day. It just means what's happening as you go way far in one direction. That's why there's 4 of these, because we have 4 directions to go. 2 on the x, 2 on the y, 2 that go positive, 2 that go negative. Nothing more than that. Okay. So let's use and practice some of this right here. So we have, let's say we have a function, and I'm just going to draw something generic. Oops, right there. Let's go. There we go. Let's draw something like this. Okay. And make it a little bit more. Let's see. No, that's why. Okay. And it says the input increase without bound. What direction on the corner plane will we move? So the inputs increase without bound, that would be talking about right here. Inputs are x without bound. Increasing would be to the right, so that would be moving right. All right, and then we have the inputs are decreasing without bound. What direction is that? So inputs, once again, x. Think inputs, always think x. All right. Decreasing would be to the left, right? So we're going for here forever. That's going to be moving to the left. And we could say to the right towards infinity and to the left towards negative infinity. And then we have, let's see here, outputs increasing without bound. That would be, outputs would be the y, right? Increasing would be up. And then we have decreasing without bound, the outputs, so that would be going down. We have to know when we see these phrases what general direction should we be looking for the answer? Okay? So how we would say this in our language, right? We would say x is approaching positive infinity. Here we would say y is approaching positive infinity. X is approaching negative infinity, and y is approaching negative infinity. So these inputs are increasing without bound is the same as saying as x approaches infinity. Okay, moving to the right on a graph. Okay, those are all synonymous with one another. So we're just establishing this language so we can use it moving forward properly. All right, so let's put it all together. It says the end behavior of a function. Okay.
Good morning, second student.
All right. So the end behavior of a function describes what the y values, y/f of x values, of a function are doing as the x values increase or decrease. So we're going to say, well, as x gets bigger, what happens to y's? Do they go up or down? Or as x gets smaller, right, decrease without bound. What happens to the y values, f of x values? Do those go up and down? Right. So, and to break that apart a little bit, the left-hand behavior, or the behavior, describes what the output values are doing as input values decrease. Right. So as the x values get smaller, without bound, which means forever, right? Visually, this would be what's called the limit of the graph. If we take the function to the limit, or look at its limits, which means look at the far outsides, right, what is happening? Same thing with the right-hand behavior, right? That just means as we go towards positive or increase without bound, that would be the limit on the right-hand side, the right-hand limit. What's going on over here? Does it go up or does it go down as x gets infinitely big and infinitely small? So just some more jargon, and that word limit, we'll keep using that over and over and over to describe basically what's happening at infinity, right, for now. All right, the graph of the right represents a function g of x. Use the graph to answer the questions below. So we'll just describe this, okay? As the input values increase without bound, what are the output values doing? Okay, so as we increase without bound, so as we go this way towards infinity, as the x-axis goes towards infinity, does this graph go up to positive infinity forever, or does it go down to negative infinity? Okay, so the way we actually write this and say it is that if I want to say as x goes to forever to the right, we're going to say as we look at the limit, as x gets increasingly close to positive infinity, right, what happens to the y values? Right, they increase without bound, which means this y values, if we just keep on following this arrow forever, it's just going to go higher and higher and higher to positive infinity. It's going to equal positive infinity. So that's how we write that jargon down using math language. Okay, and that's the same thing as saying they are increasing without bound. Right, this positive infinity means it increases without bound, the y values. Same thing here. As the input values decrease, so as we get closer and closer over here to negative infinity, so as the limit, as x approaches negative infinity, what's happening to the y values? All right, the y values are going to go infinitely down forever. So the y values go to negative infinity. So we have the x down here, right? This is the right or left side. So we're looking at this. This will tell us, are we going to the right forever or to the left forever? And these tell us what the y values are, what direction the graph is going. So if you want to look at this as negative infinity, that's the same as, the graph's going down. So if we were like in an earlier class, we'd say, what's happening at the end? You'd say, oh, it's going down. As we get closer to calculus, we don't say it goes down. We say it approaches negative infinity. Right? So it's the same concept you would say anyway. We're just calling it by a different name. Instead of up and down, we're saying negative infinity, positive infinity, or approaches. Okay? So just to break that down a little bit, there's a little bit more jargon. So On the bottom here, for now, we're just going to look at end behavior is always going to be as x approaches negative infinity, positive infinity. And your answers on the right-hand side are going to be positive infinity, negative infinity. Okay, so that's always going to be the case. So you can have any one of these x approaches infinity could have infinity as an answer or negative infinity, because remember, all this says is the graph goes up. This means the graph goes down as you look at the right side of the graph. That's all this means. Okay, it's just a fancy way of saying something we already can just look at the graph and just say. We're just writing it a slightly different way. Okay, and just to fill this up a little bit, so for this particular function, and we kind of already did it right here. Right, we'd say as x approaches negative infinity, right, g of x goes towards negative infinity. Right? How to write that out? We'd say the limit as x approaches negative infinity, and we're actually going to put the name of the function here since they're asking about g of x here. Of g of x, right, that's going to equal negative infinity. So I just added this part in because we have the name of the function. And if we look at the right-hand side, the positive side, as we go to the right, x goes to positive infinity. That's just the same as we go to the right forever, the graph is going up forever. Right? So as we go to positive infinity to the right, the graph goes to positive infinity up forever. Right? So we'll say the limit as x approaches positive infinity of g of x, that's our function we're working with, that's going to equal infinity. Just means as we go right here, as we go to the right forever of this function, this graph goes up forever. That's all this is saying in a lot of mathematical jargon. Okay? Let's see how we actually use this. Okay, so let's look at some power functions here. Eventually rise or fall without bound as x moves towards infinity, which means left or right. The behavior can be determined by a couple things that we've been looking at. Of course, the degree. So if we know the shape of the graph, like a third degree and a fourth degree, we can kind of already know what the graph is going to do at its endpoints, right? Especially if we know if it's even or odd, that what we just looked at. If we know it's an odd function, one side's going to be going up, one side's going down. Where it's an even function, both are going up or both are going down, right? And you also need to look at, let's say, like your leading coefficient. Okay. Leading coefficient. Coefficient. Is it I-C-I-E-N-T? Yeah, coefficient. We got to look at both of those, right? So we should be able to look at this at this point and say, well, we know this is a third degree polynomial, right? This is a third degree. This is x to the third. It has two turning points. That's one way I know, because it's always one more than the number of turning points. All right. It has one change of inflection, or point of inflection. It goes from concave down to concave up. That's another way of knowing it's an x to the third. Right, but we should be able to look at this and say, yeah, that's a third degree polynomial. Right? Now, is the leading coefficient positive or negative? So we just have to know from practice that this is a positive. If you just graph x to the third and had a bunch of other stuff after it, it's going to have this general shape where the left side, as x goes to negative infinity, right, goes down, and the right side goes up to positive infinity. Whereas we have to the right-hand side, this is just the reflection over the x-axis, right? This is a negative coefficient. And you could try this by putting your graphing calculator and just type in a negative x to the third with a bunch of stuff after it, and you'll see the left-hand side is always up and the right-hand side is always down. Right? These are just things we can always count on to be true. So in this case, as we approach negative infinity, as we go towards the left, right, f of x is going to go up. It's going to increase. Whereas positive infinity, we're going to decrease, go down forever. So that is, overall, these are odd functions, right? This is odd functions. One side goes up, one side goes down for odd functions. Always. Then we have, let's look at even functions. You'll notice that even functions, both sides goes up or both sides go down. Right? And we can tell we have 3 turning points. 1, 2, 3. That makes this a 4th degree polynomial. Right? It could have anything after this. It could have like minus x to the third or plus x, 22x to the second. Doesn't matter what comes after it. The fact that this is the highest degree gives it some sort of version of this shape. Right? So, and this would be considered an even function. Also follow this. Not that this is an even function, but all even functions will follow this. Right? This is close to even function, but not quite. So, but both sides, you can see here, with a positive coefficient, have that W shape. Right? This has that W shape. So x to the 4th always has that W shape, whereas a negative x to the 4th, right, has the reflection of that, right? It's reflected over the x-axis, so we have an M shape, right? In that case, let's say like this, M shape, both sides will go to negative infinity. Both sides go down forever. Remember, all this negative infinity means is it goes down. Positive infinities just means it goes up. Left side, right side, it goes up, it goes down. Just a fancy way of saying that. And just to summarize down here, yeah, odd degrees, right? Graphs open in opposite directions. Opposite directions. Whereas even, same direction. They open in the same direction. That's the takeaway from this. Right? These are 4th degree, right? Even degrees. Both open up, both open down. Odd degrees, one up, one down, no matter what. Okay, so consider the domain and range for each degree family. All right, so as x approaches infinity and x approaches negative infinity, what do you notice about f of x, or the y values of the graph? Right? So another way of looking at this, of course, is that if they go the same direction, right, they have the same answer. That's all that we're asking, right? If they go opposite direction, they have opposite answers, right? One's positive, one's negative. So just another way of phrasing this, just to make, full sense of everything. So we can write this a number of ways, but basically that's the sentiment. So for even powers, you can say like n behavior is the same. Right? We can say odd powers. And behavior is the opposite. Okay. It says, how does the value of the leading coefficient A affect the answer? Right? So if the positive, even powers are both up, but with negative, they're both down. Odd powers, right? The graph has a left side that goes down, right side goes up. But if we make a negative x to the third, the left side will be positive infinity, and the right side is going to be going down. I'm just describing these 4 graphs right now. All right, so we're just putting that sentiment into words. All right, so you can say if we put a number away, but we could say basically if A is negative, right? If the value is negative, the leading coefficient, well, I will say if A is negative. Right, just because they gave it a name here. So if A is negative, right? By the way, you could say this a number of ways. You could say, well, if A is less than 0, of course, that's the same thing as negative. That's fine. Then the n behavior is the opposite opposite of when a is positive. A is greater than 0. Okay. Good. So let's look at some of these here. It's a little smaller so it fits. There we go. So we have some functions here, right? And we're talking about the end behaviors, like we just mentioned. We're not really worried about anything else this function has to offer. We're just looking at the end behavior only. So I'm not sure how high and where the mins and maxes and the zeros are. Okay. However, I do notice that this is a n degree, right? So that's a 3. That's a 3 right there. And I do notice that the term here, right, is negative. A sub n is negative. So I do know it does this shape of some sorts. Not sure, where again these zeros and mins and maxes are right away, right? But I can describe the end behavior, right? And if I want to get more specific, I can. Okay. So I do know if as x goes to negative infinity, we're going to go up. That's going to be positive infinity. As x goes to positive infinity, as we go right, the right side of the graph goes down. Okay. How many turning points are there? Always one less than the degree, so that's 2. And this is not an accurate graph, but it gives me the information I need to know for the end behavior. All right, we have, let's see here, an even degree, so I know this is going to be like a W shape. So something like this. I'll be a little more careful here. There we go. A W shape, right? It's a 4th degree. And we know it is positive on this one, right? There's positive here. So we know it's W, not an M. Which means on the right side, this just means left side here. This means right side. Negative infinity is left. Positive infinity is right. Both sides, the graph goes up. Positive infinity. Turning points, 1, 2, 3. One less than the degree. All right, so most of this is how we're writing our answer. The math here is like you just have to be able to subtract, subtract 1 from 4 to get the number of turning points. So it's not really a lot of math here. We're talking about language. We're talking about what things mean, right? Very different type of thing we have to focus on. Okay, so this just summarizes what we did before. The graph of f has at most n minus 1, 1 less. From 3, there's 2 turning points, right? And the function has at least n real zeros. Oh, at most, sorry, at most. Because it could have imaginaries. It could have imaginary roots. So, like for this x to the third, at most it can have 3 real x-intercepts, right? But the graph could look like this. It could go like this, right, and only have 1. And that means it has 2 imaginaries. So, at most, you can have whatever the degree is, number of real roots. All right, so it says, let's increase this a little bit more. For a polynomial g of x, the limit as x approaches negative infinity, as we go to the left, the graph will go up. Right? That's what this says. As we go to the left of this function g of x, the graph goes up, positive infinity. Okay? As the graph has an odd number of turning points, what can you conclude about the leading coefficient? So it has an odd number of turning points. Let's say 3, and the left side goes up. So I'm going to say this is my left side of my graph. It's up here, and I have 3 turning points, right? Let's say 3. So I'm going to do 1, 2, and then 3. It has to go back up. So that must mean you have an even degree polynomial. Okay? So if I did this with 5 or 7, I'd still get 6 and 8 degree. Right? So it doesn't matter that I used for my example 3 and got 4. It'd always be 1 more. 1 more than any odd is going to be an even number. Right? So we can say something like if g of x has an odd number of turning points, then the degree will be even. And yeah, I think that's about it. Oh, and looking at the leading coefficient. Well, here, of course, since it's moving up, we can say and the leading coefficient is positive. All right, that's pretty good. Description, and you can add a little bit more or a little less. Just depends on what you want to say, but that's definitely suffices in that sense. All right, so we'll go down to number 3. All right, the polynomial p of x has the following characteristics. The left side goes down, the right side goes up. Left side goes down, right side goes up. So sketch a possible graph. Okay, we can do that. And it can look, so that means just the left side here. Left side goes down, and the right side goes up. And we can put anything we want in the middle. Anything at all. All right, so I could do this. There we go. Because the left side goes down, the right side goes up. I could say this. That's just a regular third degree. Right? I could be, something like that. Left side goes down, right side goes up. So anything, just as long as the end behavior, right, is what they dictate, then you're good to go. So I could just give this label of p of x. Right? Doesn't matter. Any version you want to do is totally fine. As long as it's a function, it's okay. All right, number 4, the function h is given by that polynomial. Determine the end behavior. All right, we have a 6th degree. Right, we have a 6th degree, so that's even. Right, even and positive, which means both sides are going to be going up. Right, and there'll be 5 turning points. So we can have like 1, 2, 3, 4, 5. Right, something like that. 1, 2, 3, 4, 5. Yeah. So we can see that both sides go to positive infinity, right? So we can say the limit as x goes to the left equal, and I'm going to put h of x here. So it gave me that function name. It goes up, and the limit as x goes to positive infinity of h of x goes up. All right, good. Let's see. Go back down. Lastly, I think we're almost there. Okay, write a following in the limit notation as x decreases. Limit, right, as x decreases, which means negative infinity, without bound, p of x increases without bound, which means goes to infinity. Okay, and lastly, let's just do the reverse. Write a following in words. So we're going to basically write one of these statements right here. Just do it the other direction. So we're very comfortable with this. So use this as a model. This time we see positive infinity, right? So instead of decreases, it's going to be increasing. So let's go to black. Okay. So we can say as x increases without bound, t of x in this problem decreases, because this is negative infinity, decreases without bound. Perfect. All right, and that's it for this lesson. Okay, mostly just jargon and what's happening as we go to the left and go to the right. Does the function go up or function go down? And all the little fancy, little hints we can use to figure that out.